Hello, I'm Pierre. I'm the CEO and co-founder of C12. We are a quantum hardware startup based in Paris. And our profound conviction is that we need to build quantum computers differently. Different by design and different from the first qubit you built to the millionth one. That's how we build the future of quantum computers. So we don't have quantum computers yet. We don't have them yet because they are bugged with errors. We don't have them yet because it's even worse. These errors increase when you scale the number of qubits. We don't have them yet because actually we are trying to optimize approaches without having the right material. And the fundamental challenge to build this revolutionary machine is that quantum material interact very easily with our environment. It's a very simple fact. All these errors, they come from defects in the qubit material. No defects means no perturbation. No perturbation means no errors. And I think there is a large consensus now in the scientific community and in the quantum industry that this is the most important challenge to overcome in the next years. And I pick one quote from a great scientist I admire, Chris Monroe. And what is he essentially saying is that if we want to build a large-scale quantum computer, we need a breakthrough in terms of material. At C12, we leapfrog this materials gap by powering our quantum processors with carbon nanotubes. We use this elementary and ultra-pure material for making our qubits. We are transforming this carbon nanotube into quantum transistor. So carbon nanotubes have extraordinary properties, and they kind of solve the quantum paradox, making qubits very isolated, yet addressable. Our vision is that carbon nanotube will power all quantum processors in the future because they are the equivalent of silicon for classical computer, the enabling material. We are designing the form factor of next generation quantum computer. So silicon enable the emergence of all our semiconductor industry, our smartphone, and our laptops. It's now time for carbon to do the same for quantum. This is our vision. Now, what about the numbers? Where are we in terms of quality? Why carbon nanotubes? Here is our qubit. So we encode our qubits in the spin of a single electron trapped into a suspended carbon nanotube. The trap is made by semiconductor gates, so it's a semiconductor technology. And it's a very fragile system, like any other quantum system, and we need to protect it from all the sources of errors. There is actually only 3 sources of error. The first kind of perturbation are magnetic perturbation. They come from nuclear spin. The second is electrostatic perturbation, and the last one is mechanical perturbation of the carbon nanotube. So, what are the numbers on protecting the qubit from all this source of errors? On nuclear spin, we can actually purify our carbon nanotubes. So that's actually why we are called C12. And we can have less than 1 nuclear spin per qubit, which is 2 orders of magnitude. That is what you can do best in other quantum platform. On the electrostatic perturbation, or what physicists call charge noise, we recently demonstrated that actually a suspended carbon nanotube is the best protection against charge noise. This measure was performed by our collaborator at University College London, Mark Butler. And it's actually also 2 orders of magnitude better than what you can achieve in CMOS silicon. And the last one on the mechanical perturbation, what is happening is carbon nanotube is a 1D system, so you have confined mechanical or vibrational mode, and you can really well uncouple from them. and so we can have also like extra long relocation time because of those mechanical perturbation. So of all of the Descartes channels, to our knowledge, there is no other solid-state platform that can achieve such levels. We set world records on all of them. That's a very good start to make a qubit. But the race to make a quantum computer is much harder, because then you need to scale the number of qubits. What our, let's say, much profound conviction is that the race doesn't look the same if you start with the right solution by design. So what about the end game? To implement useful quantum algorithm, you need two things: high-quality qubits, but also a lot of them. So here I measure the quality of the qubit in terms of current time is my y-axis, and in terms of x-axis is the number of qubits. What is great about atoms and ions is that their qubit lies in vacuum, and so they are very good qubit, very high current time. The problem is that they are facing a very fundamental limit to have quantum system with more than 1,000 qubits. On the other side, you have superconducting qubits. What is great about them is that it's a chip-based technology, that it's compatible with semiconductor fabrication techniques. The problem is that they have reached the limits in terms of physical current time. So that's why also that these players are mostly focusing on quantum error correction. But quantum error correction is much, much harder if you start with a poor quality qubit. You will need more physical qubits to actually create a logical qubit, so much more overhead. So we have a very different approach, an elegant approach, where we focus on delivering high-quality physical qubits. And in a way, what we have done and what we are building is that we combine what is best in the two other worlds. So the manufacturability of a semiconductor devices with this unique feature of vacuum that we bring onto a chip. Because at the end, our solution is an ideal spin qubit in vacuum. So thanks to this very unique approach, we will be able to deliver to quantum developers quantum computers with unprecedented capabilities in terms of fidelity, in terms of scalability, and also extra feature in terms of connectivity. So introducing this revolutionary quantum processor. So we achieve high fidelity because of this new material that we use that protects qubits from errors. Our fabrication process is scalable because it's compatible with industry-proven semiconductor fabrication techniques. And last, connectivity. So connectivity between the qubits, it means that we can minimize the number of quantum operations to perform algorithm, but also reduce the overhead that we need for quantum error correction. About fidelity, what about the numbers? So our first generation will offer 4.9 fidelity for the 1 qubit gate, and the 1 qubit gate duration is like 80 seconds, sorry. And for the 2 qubit gate, we can achieve 3.9 fidelity with a gate duration of 500 nanoseconds. This is 10 times more than what you can achieve with commercially available quantum devices. How we solve the manufacturing process is by using this unique nano-assembly process. So on one side, we fabricate the silicon chip with the electronic circuits, and on the other side, we fabricate the carbon nanotube, so the qubits, and only at the last step of the fabrication process, we integrate the carbon nanotube on this silicon chip. This is fully electronically controlled and can be fully automatable. So what is also important is that the quantum material does not see any processing step before the last one. I often got the question, actually, why we don't have other startups developing carbon nanotube-based technology. And this is because of this patented nanoassembly process. The blocking point of this technology was how you manufacture devices, quantum devices, with carbon nanotube. And we are the only one mastering this very complex nanoassembly process. And last, I would focus on crucial component of our chip. It's a quantum bus. So this is actually the black lines that you can see. It links the different carbon nanotubes, so it links the different qubits between them. And this enabled two things. One, we can offer long-distance spin-spin coupling. So we are not constrained by nearest neighbor interaction. This solves a big problem in making quantum computers because it minimizes crosstalks. So the errors do not grow exponentially when you scale the number of qubits. And the second thing that it offers is high connectivity. So we can have like modules of a group of qubits with all-to-all connectivity. This is also something very important for scaling. We are starting with 1 qubit and on the road to build a quantum processor that will deliver 1 million qubits. So as I mentioned, we are based in Paris. We are a spin-off of the École Normale Supérieure after mostly a decade of research on this material. So with Mathieu, my twin brother, we founded C12 in 2020. We are now 30 people, incredibly talented scientists and engineers. And we are backed by deep tech VCs and also like corporates. We have now a portfolio of 6 patents, both on the design and on the manufacturing process. So at C12, we are first building a quantum coprocessor. Our C12 chip will be integrated into a classical environment, and it will offer a hybrid quantum classical algorithm. That's where a minimal part of the quantum algorithm will actually run on the quantum chips, minimizing the number of steps and avoiding the limit of decurrence. That's interesting because for a long time, it was thought that we need perfect computers to do something useful. But now we know that we can run some useful algorithm on imperfect quantum machine, especially if you have enough fidelity, and this is really where we focus on, and for example, for application in quantum chemistry. So by 2025, this will correspond to the largest, actually, quantum market segment. And so quantum machine will have limited number of qubits, and no error correction, but high quality physical qubits. So again, first focusing on the quality and then the quantity. We then scale the number of qubits to offer a full error-corrected quantum computers, and the quantum error correction will correct the residuals errors. And this year, we release our first product. It's a digital twin, so it's a simulator of our future QPU. So how we integrate in the full quantum computing stack. We are really a hardware-focused company, so what we deliver is a quantum chip and a low-level control software. It's really like NVIDIA focusing on the GPUs and CUDA, which is the low-level control software. But what is very important is that we are compatible with all the main SDKs, so like Qiskit, because we are supporting OpenQuasm, and also Ticket. This will be both for our first digital twin and later on for the QPU that will offer those unprecedented capabilities. So as I mentioned, this year we release our first product, which is a digital twin. And when you look at what is available in terms of simulator currently on the market, either you have perfect simulator, it's interesting, but it's more like for long-term development, or you have noisy simulator. But those noisy simulator, they only like add always the same probability of errors for every gate. So we think about this simulator and the digital twin in a completely different way. What we did is that we model all the physics phenomena that occur during computation, and we model and program them into our digital twin. So we will be the first company to provide such a resource, such an accurate copy or mock-up of our future quantum processor. And we think that this is very important to test actually quantum algorithm that will be developed by quantum developer and study the scaling law. And also, like 2025 is not that far away. So we have also designed a like very structured, step-by-step process for forward-thinking company that would like to be ready when actually quantum advantage will be there. So first about like working with them on identifying the use case that will be relevant for our technology, then testing actually the quantum algorithm on our digital twin, and then working on delivering the quantum computer. So first the layout, and then the making of the quantum computer. And for example, we are supporting Air Liquide in their quantum journey. Air Liquide is one of the largest gas manufacturer, global gas manufacturer. And we are developing the hardware where Quantinuum is our partner in the software task. And what I really like about this project is that we were able to identify a use case that is both relevant for our near-term hardware, but also has a very huge business impact. So Air Liquide is providing gases for the semiconductor industry. And one of the key challenges of the semiconductor industry is to go for more advanced node. And to do that, they need to deposit different kind of metals. So they ask Air Liquide what there's the right gas precursor to actually deposit the metals. This is not a problem that you can simulate on a classical computer. So it takes years actually for Air Liquide to find and to identify the right gas precursor to deposit those new kind of metals. What we are developing with them is a quantum computing-based approach that can really solve this problem. So with our tech, this could be completely different. Thank you very much.
Okay, we have time for about one question. Do we have any questions for Pierre?
I think there is one question in the back.
Just have one question. How do you move the qubits?
How do you
move the qubits?
Oh, so the qubits are fixed. So the electron, when they are trapped in the carbon nanotube, are fixed. And yes, I did not enter into the detail of the physics, but those quantum bus, they don't move the qubits. They move actually, it's a microwave, so it's photon that actually mediates the interaction between the spin. And it's not even photon, but it's a vacuum fluctuation of this resonator that enable the coupling between the distant spin. So it's a cavity quantum electrodynamics mechanism.